my name is Molly. I'm a third-year honors immunology student at McGill. I'm the project manager of the drone project. This is my third year with McGill Robotics, and my first year with the drone project. On the flight line, I will be in charge of coordinating between the flight line members and the judges, as well as taking footage.
Hi, my name is Anas, and I am a graduating electrical engineering student. I joined McGill Robotics 5 years ago and have been leading drone software efforts for the past 3 years. This year, I architected and oversaw all software development. On the flight line, I'll be supervising all ground station operations and making sure everything goes smoothly.
Hi, my name is Babe, and I'm a graduating electrical engineering student. I joined McGill Robotics 5 years ago, and I have been the drone electrical lead for the past 2 years. I have designed and implemented the aircraft's electrical system, ensuring safe and reliable operations. I will be at the front line to debug potential issues and to make emergency repairs.
Hi, my name is Jad, and I am a second-year mechanical engineering student at McGill. This is my second year on the team, and I am the mechanical division lead of the drone project. I spent the past year working on designing and building our competition airframe. On the flight line, I'll be in charge of overseeing the UAV's setup and disassembly.
Hi, my name is Yasasa. I'm a third-year electrical engineering student. I've been working with McGill Robotics for 3 years, and this is my second year on the drone project. This year I worked primarily on the software and more specifically the obstacle avoidance. And that's exactly what I'm going to be monitoring on the flight line.
Hi, I'm Elsa Riashi. I'm a graduating electrical engineering student. I'm on the software section of the drone team working on computer vision.
Hi, my name is Chun Wei, and I'm a second-year student of electrical engineering. I have a year of experience with UAVs on the drone software sub-team. I worked on the interrupt client and the mission planner, and those are the things I'll be monitoring on the flight line.
Hello, my name is Michael Krasenko-Vita, and I'm one of the mechanical members on the team, as well as a safety pilot for our local flight tests. This is my third year on the drone team. On the flight line, I'll be communicating with the competition safety pilot and acting as a spotter.
I'm Matthew Phillips, and I'm in my third year of mechanical engineering, and I'm minoring in software engineering. It's my first year on the team, and I have experience in aerodynamics and carbon fiber manufacturing. I'm on the mechanical sub-team, and I've helped with various things, including helping with the design of skis for winter testing. On the flight line, I'll be helping with plane setup.
I am Alev Orfi. I'm a second-year student in Honors Math and Physics. This is my first year on the team. I've had no previous experience with UAVs. I'm in the mechanical sub-team, and this year I worked on the air delivery system.
I'm Jean-Edouard Lecourt, U2 student at McGill University in mechanical engineering. I'm part of the mechanical team of drone, and I've been working on fabricating, designing, and manufacturing some parts. I have some experience in aerial frames that I've acquired on my own, but this is my first year and I'm very excited.
Goonie 4 is a fixed-wing twin-boom pusher aircraft and McGill Robotics entry for the competition. It is a ready-made RC Anaconda that has been modified according to our needs and fitted with all the required hardware, including an onboard computer, a gimbaled camera, and all of the necessary avionics. Components are mounted on detachable 3D printed bays, allowing for modularity and ease of access.
Goonie 4 employs a 6-cell, 13 amp-hour lithium polymer battery to power a 365 kV motor with a 15 by 10 inch propeller. An Intel NUC is used as the companion computer alongside a Pixhawk 2.1 autopilot. The software system runs on the PX4 flight stack and the robot operating system. The system was designed to operate fully autonomously and does not rely on any communication to the ground to accomplish competition tasks. Everything runs on board the aircraft, and the ground operators will only serve to guide or modify its behavior when they see fit.
Goonie 4 will attempt to perform all competition tasks. Our degree of confidence with each task, shown in this table, is based on the extent of testing done and performance during tests.
Our development process also relied on a software-in-the-loop simulator, integrated with Gazebo. It is capable of simulating all mission tasks, and can randomize them to all to our liking. Moreover, a continuous integration server automatically runs all unit and simulated mission tests before any change can get committed. As such, we could test and iterate very quickly and minimize flight test crashes due to easily avoidable problems. In addition, the team relied on a smaller surrogate airframe, Goonie 3, for testing software without risking the competition airframe. Over the course of the year, it accumulated multiple hours of flight and proved instrumental in validating newly written code. Finally, only once all of our automated tests had passed, and once we were confident with its performance on Goonie 3, were we ready to conduct similar tests on our competition plane, Goonie 4.
Has consistently flown every weekend over the course of the year. Winter testing was principally done using Goonie 3, with increased Goonie 4 testing later in the year. All of our flights were fully autonomous, except when testing new airframe setups. Additionally, since we used an off-board planner, the only required autopilot side tuning was limiting the controller flight angles. Everything else is adaptive.
This year, we managed to get a very good obstacle avoidance scheme that can avoid both moving and stationary obstacles in real time. This was achieved with a local planner known as the Dynamic Window Approach, or DWA. This planner works by simulating a set of controls at every time step, then choosing the best one based on criteria that we provide. We decided to penalize any control that went too close to a moving or stationary obstacle. On top of this, we rewarded controls that tended to face the goal. The end result of this is that the plane will always go towards the goal, but will always automatically dodge any obstacles in its planner. To further improve our results, we predict moving obstacles' trajectories nearly perfectly 10 seconds into the future, and incorporate the predictions into DWA's simulations. We have extensively tested our planner on a multitude of randomly generated moving and stationary obstacles, with 100% accuracy. We have also tested this on our Goonie 3 testbed, albeit not as exhaustively. Another advantage of our DWA planner is its increased waypoint accuracy performance, as we no longer need to rely on the PX4's L1 controller. This gives us complete control over how accurately we want to hit our waypoints. For now, we set our acceptance radius to 15 feet, which our DWA planner will continuously attempt to hit. As such, we can hit 100% of waypoints within 15 feet while avoiding obstacles. We have tested this exhaustively, both in simulation and in air on Goonie 3.
Using the Point Grey Flea 3 camera with an 8mm lens and flying at an altitude of 120 feet, the smallest possible target, 1 foot wide, would take up 60 pixels. Our tests have deemed this sufficient. Moreover, to ensure the best image quality, we have tuned our gimbal controller to stabilize the footage as much as possible. We trained a sliding window classifier, which extracts features from a window using a convolutional neural network and classifies whether that window contains part of a target. The windows with a positive prediction are used to compute a box around the object. We trained and evaluated the detection network on generated data obtained using the gazebo simulator. Our validation accuracy on generated data is around 98%. We anticipate that our model's performance will be much lower on real-world data, which is why we have implemented a domain adversarial model. A few real targets were crafted in order to collect real-world data. However, due to difficult weather conditions, not enough images with the Point Grey camera were collected yet. Evaluation of target attributes is achieved through a combination of k-means clustering, OpenCV's contour finding functions, and Tesseract OCR, which have similarly promising results on our simulated data. Over the next week, we will be collecting more real footage for our domain adaptation. Based on our aircraft's estimator's average converged covariance, our estimated standard deviation would be approximately 5 feet. This means that we have over a 99% chance of localizing within 15 feet of the target. Our gazebo simulations on thousands of generated targets coincides with this measurement error, but we have yet to validate this in real life.
The air delivery system is mounted on the bottom of the plane and drops the bottle when a servo lets a restraining latch loose. The bottle breaks on impact without needing any modification. We have a simulation going for the airdrop at all times, which estimates the location the bottle will hit. When the estimated position of the airdrop is close enough to the target, we will release the bottle. We assume constant wind speed and direction during the fall for the estimation. We were able to easily test this in our simulator as shown here. In our test trials, we were able to deliver the airdrop package within 15 feet of the target 80% of the time. So far, our full mission tests have been limited to simulations since Goonie 4 cannot take off or land in Canadian winters. Moreover, the extreme cold limits Goonie 3's battery life to 3 minutes, which is insufficient for a complete mission.
Instead, a number of isolated tests were carried out to validate the design. This allowed us to gather valuable operational knowledge as well as identify any flaws with the initial setup. Problems were identified with the front landing gear and camera gimbal. Consequently, the landing gear was redesigned and replaced, and the gimbal was remodeled to have better balance. Now that we have validated GUNI 4's mechanical design, and that weather finally permits, we will be focusing on more exhaustive full mission tests until competition. Based on our full mission tests, we estimate that we will get 40% for the mission time criteria, as we have averaged 25 minutes while performing the full range of mission tasks. We also do not expect any penalties or timeouts, as we never go over the full 45 minutes competition period. For the autonomous flight task, our tests show that we should receive full marks for both the autonomous flight and the waypoint capture sections, as we never go out of bounds while hitting 85% for waypoint accuracy. Moreover, our tests show that we should expect full marks for the obstacle avoidance sections of the marking scheme. Along the same line, we expect 75% or more for all object detection, classification, and localization tasks. As for air delivery, our tests have shown an average of 80% accuracy. Finally, due to us not suffering any major crashes and due to last year's performance, we expect 80% for operational excellence as well. Overall, we expect our total mission score to be over 80%.